Hello, in this video we'll speak about solenoid, which is one of the most famous form of electromagnet, and it's also one of the simplest because it's just composed of current carrying wire. So we will use Python to first parameterize the coil using the Plotly library. Then we will do analysis of the magnetic field by calculating the homogeneity and mean magnetic field using Magpylib library. And then we will visualize the field in 3D using Plotly and Magpylib libraries. During the process, we will use Jupyter Notebook, and I want to note that the code will be accessible via GitHub. So here we are in Jupyter Notebook, and first we will import the necessary libraries, which include the Magpylib, NumPy, Matplotlib, and Plotly. Then we will define our initial parameters. So resolution is the number of discrete points used to approximate continuous curve. The bigger the number, better the approximation, with an important caveat that it will make computation slower. So here we set it up 750. Then it's radius in meters, as the current version of Magpylib is for SL units. And then we have the length also in meters, and layers, which I will set 1 for now, which is the number of full windings along the solenoid, which we will better understand after visualization. Diameter is the diameter of individual wire. Turns is the number of turns. Plotting is a Boolean variable which we will use to enable or disable the showcase of the plots, and current here is also given in amps. And this figure we use to enable the use of Plotly library. To define or parameterize the solenoid, we can refer to Magpylib's documentation, where we have a simple example of solenoid. So let's first copy this and run it here. So here we can see the plot. However, this is a simple example, and later we will want to improve this. So for that, let's use our own variables and parameterize it using common variables like theta and radius. Another note is that the values here are hard-coded. However, in the future, to make the code more robust and reusable, we will need to use our parameters, which we just defined here. So for that, I will delete those parts and use the common names for variables. So let's start with theta, which goes from 0 to 2 pi times the turns and is sampled as at resolution number of points. Then we have the z, which is again can be parameterized using lean space function, and z starts from the minus of length over 2 to length over 2. This is to have it symmetric along the 0 xy plane, and again number of points here is the resolution. So now when we change the resolution here, we would also change it here as well. Then our x coordinate would be r times cosine theta, y would be r times sine theta, and z would be just z. So the coordinates, to pack them into a single array, we can use np.stack function and stack x, y, z along the axis 1. So np.stack will create a new dimension where we will have x, y, z paired together. And then in our coil 2, we can rename this to solenoid. And current is the current, so we use our current. And instead of vertices, we can just input our coordinates. And then we can use this solenoid.show. So when we run this, we see now the solenoid changed with our own parameters. The radius is 4 centimeter, which I can change to, let's say, 6, and then run again and see that the solenoid changed. We can further improve this solenoid by adding layers. So when we add more layers, basically we create more coils, which are separated by wire diameter. Or another way to say it is that we offset the original coil by a distance equal to wire diameter. So for that, let's iterate over the layers. So I'm creating a for loop and putting everything we wrote here into that for loop. But before iteration, we need to create some empty lists which will hold the values of all iterations. So for that, I will create coils, which is just an empty list for now, coordinates, which is again empty list. And another important thing we need to account for is the layer current. As the original current is unchanged, adding more layers will distribute the current evenly. So for that, layer current will be just current divided by layers. So the theta and z will be unchanged. However, in parameterization of x and y, the radius will be incremented or increased by diameter at every layer. So for that, we'll just change r to r plus I times diameter for x and y. So now when each e variable is a separate layer, the coordinates is no longer the total coordinates or the full coordinates, it's just layer coordinates. And in this layer, it's not right to call it solenoid because we are not creating the solenoid in a single layer. Solenoid is composed of many layers. That's why we will call this as individual coil or coil layer, which will take the layer current as input, and its own vertices would be the layer coordinates, not the whole coordinates. Another thing we need to change is to remove this solenoid.show out of the for loop for now. In order to save the coil layer created per each layer, we can append them into coils list, which we created here. So we can just write coils.append and input the coil layer. This will make sure that after each iteration, the coil layer is saved in the coils list. And also we can save the coordinates or create a stack of coordinates to save the whole coordinates instead of just individual layer coordinates. So for that, we will use the vstack function from NumPy. So coordinates is equal to mp.vstack. So here, why we are using vstack instead of stack? Because we don't need an additional dimension. We are just stacking them vertically. And then here we will input layer coordinates. So after our for loop, when we have the coils, which is a list composed of coil layers, which are Magpy object, we can bring them together into a solenoid by using Magpy's collection function. So for that, we can write solenoid is equal to magpy.collection and input the coils. So this will create the final solenoid, which we can just visualize by using the .show function. So let's run this. So here we see the same results because we didn't change the initial parameters, but our effort to add layers will be visible when we change the number of layers from 1 to, let's say, 3. Then when we run again, now we see that the solenoid is composed of 3 layers, so there are like 3 coils at each turn, and with these arrows we see that the current flows the same direction because at the end they are connected. We can also go beyond 3 and let's say make it 10 and see that it becomes thicker. So here we see how adding more layers improved our parameterization, because in real world solenoids have more than one layer. So here I added a few more lines of code for plotting, and here I want to demonstrate that beyond the Magpylib's default plotting, which use the show function, we can also utilize plotly library, which we imported here, and have more interactive 3D plots in the browser. So let's run and see the difference. So here we see that it's more interactive, and another nice feature of this is that we can enable or disable several layers. So let's say if we just want to see the layer 1, we can disable the rest. And now we are only left with layer 1, or let's say we want to see only layer 1 and layer 6. We can only enable them and see only them. Also here we can see the effect of changing the resolution. So if I go back and reduce the resolution to, let's say, 250, we can see that the curvatures become more rough because there are less points to approximate. And similarly, if I increase the resolution to 1000, the curves would be really well approximated. So now we reach to a point where this single cell is able to generate and parameterize a solenoid given the number of layers, the radius, the length, the need for plotting, and the number of turns. So why don't we just create a function out of this to make it more reusable in the future? Because with a function we can then create similar solenoids with, let's say, a different current or a different radius without running this whole code again. So it will be more efficient to just make a function out of this. Define the function here. I will call it create solenoid, which will take our initial parameters as input. So it is R, L, layers, diameter, turns, current, and plotting. And at the end, our function will return the solenoid and coordinates. And then to utilize the function of plotting, I'll just add if statements here and here. So to test our function, we can create a cell below, and let's say we want to make a solenoid 1, coordinates 1, using our function. And as inputs, we will just give the initial parameters. So also we make sure that the plotting is enabled, it's 1 or true, and we can just run this. And now we see the plot again. Also, we can create a different solenoid. So now we see how easy it's to create when we have the function. We don't need to recreate the cell again. And let's say it's the same solenoid, it's just the radius is double and the length is halved. So when I run this as well, now we see the both solenoids centered at 0. So the second one has double the radius and half the length as expected. And again, I can enable or disable any layer from here. So now let's speak about the cost function part, where we calculate the field homogeneity using this formula. So field homogeneity is equal to maximum field minus minimum field divided by the mean field and multiplied by 10 to the 6 to get ppm value. So this is a unitless, and homogeneity is defined over ROI, or region of interest, which in this case would be just given as an input in a form of decimal percentage. So let's say if we want an ROI which is 10% of the radius, we'll input 0.1. So here we have the function called cost function, which takes the max, and max is a Magpy object. So here when we return the solenoid, this is already max or Magpy object. So max is one of the inputs and the ROI. So first thing we do, we create a grid, 3D grid, which has uniformly spaced points. For that, we can use mGrid function from NumPy. So the bounds are minus ROI times R because it was the decimal form. So minus ROI times R is the radius again. Minus to plus that radius, 10 points. This can also be increased for better results, but again, it will increase the computational time as well. So here we have X, Y, and Z. And we take the transpose of the grid in order to have shape N and N free. So this is in order to make magnitude calculations easier, and also to when we use the getB function here, getB expects a shape which has the components as a last axis. So what we do here, if we want our grid or the ROI to be spherical, this is usually the case for MRI or NMR. Otherwise, it can be a cube as well. But for a spherical ROI, we can create a mask. How we do it? We define R, which is the distance of the coordinate from origin. So that's why we take the -1 or the last axis, which is this 3, which holds the XYZ components. So we input the grid, which we just defined. In this point, the grid is a cube. So now we have the distance of the points of the cube from the origin. Then we create a mask using the condition that R, or the distance, is smaller than the ROI times R. So this ROI times R is a radius again, as we said. So the sphere points, which will create the spherical ROI, is just the ROI grid with mask condition. So this mask will create a Boolean array, and when we input this Boolean array, we can create a spherical grid, or turn our cubic grid into a spherical, because the points which are outside of the sphere would have a value false, which wouldn't be taken in these sphere points. And then we can calculate our magnetic field in the ROI or BROI using the getB function from Magpylib. So that's why the mags should be a Magpylib object in order to be able to utilize this function. And here we input the sphere points, and then similarly to this notation, we calculate the magnitude B, which is again the BROI at axis -1, because again the -1 is this axis where we have the components. And then we calculate the mean field using the mean function from NumPy, maximum field again using the max function, and mean, which are built into the Python by default. And eta, or homogeneity, is the Bmax minus Bmean, as in the formula, divided by mean B multiplied by 10 to the 6. And the function returns the homogeneity, mean field multiplied by 1000, because by default the Magpylib will return Tesla, but because we are working in a lower fields, we want to multiply it with 1000 to get a millitesla, and we will also return the sphere points. To visualize the fields in 3D, we can refer to Magpylib's documentation, where we see that the sensor object with its pixel attribute can be conveniently used to visualize vector fields. And in our case, we only need the B field. For detailed documentation, we can click on this and see the code for changing some other variables. So using this code, I created visualize 3D function, which takes the grid, which is the uniform grid similar to the grid we had in cost function, and mags object as an input. So again, mags here is a Magpylib or magnet object. And here I create sensors using the magpy.sensor object, which has its pixel attributes at grid points. So the pixels are distributed uniformly along the grid. So the rest is subjective. This can be changed accordingly. And here we can see that we use Plotly as a backend, the library which we imported, and we use the browser to render the graphics. So let's run this function, and after that, now we can create a coil. So let's create a solenoid with coordinates using the create solenoid function. Let's define our ROI to be 0.1 or 10% of the radius, and our grid 3D is a 3D grid which spans from in XY plane from minus to plus 1.5 times the radius, and in Z plane it spans from minus length over 2 to length over 2, which is just the length of our solenoid. And I take 10 points in X, 10 points in Y, and 20 points in Z direction. And then I use the cost function and assign its returns to eta, mean, b, and sphere points, because as we remember, the cost function was returning three variables. So let's run this as well. And then to visualize the results, we can use the visualize 3D function by inputting the grid, which we just defined, and the solenoid object, which we just created, and we can print the homogeneity and field. So let's run this. So here we see our field lines. So we can see the result matches the expectation. So the field is pointing up inside the solenoid, and we can also see the direction of the current. So here we can reassure us in the right hand rule, and we can also see that field outside of the solenoid is quite weak, which was also expected. The rest can be changed again subjectively. So here I sampled 20 points in Z axis, but the points can be increased or decreased. Similarly, in X and Y I sampled in 10 points. Those as well can be changed. Also, we can see the results here. The homogeneity was 595 ppm in 10% radius ROI, and the field in millitesla was 0.89. Another method to assure us that things are working as expected is by changing the default parameters. So let's say here we increase the current 2 times. So what we expect the homogeneity to stay the same, but we expect the magnetic field to change, to increase. So let's run this. So the homogeneity is 595, field is 0.8. So when we run this again, we can see that the homogeneity stayed the same as expected, and the field increased again as expected. So that was it for today. Thank you for your attention.